do I record?
I can record you. So
Okay,
the
okay.
time is pretty much up and we can start. So hello everyone, today we will move to a new section on the graph neural nets. And the first paper we plan to discuss on the graph neural nets actually is more like an analyze paper. So we focus on analyzing the bottleneck of the existing graph neural nets. And the presenter today will be Yutong Wang, right? And Yutong will lead the discussion for us, about this paper. And I can give time to Yutong, and you can start when you're ready. Yeah.
Okay, thank you, Professor. So today I'm going to present a paper called On the Bottleneck of Graph Neural Networks and its Practical Implications. So since this is the first time we look into the papers talking about the graph neural networks, I'm going to give a brief introduction of the graph neural networks, but since I'm not an expert on it, so please point me out if you have any questions or I said something not correct. Yeah. So the first question is, what is a graph? So a graph is consisted of a set of nodes and a set of edges. An edge is a connection between two nodes that represent the connection between them. So, so a graph G equals to V and E. In this example of the graph, we have 4 nodes, 1, 2, 3, 4, and we also have a set of edges, which is 1, 2, 2, 3, 3, 4, and 2, 4. So in a graph, we can have different types of edges, which means an edge can have different types or different features, and each node can also has different features. And also, the edge can be either directed or undirected. So what can a graph represent? A graph can represent, generally speaking, it can represent a set of objects and the connections between them. So what kind of real-life applications can you think of? So the first graph applications can be a molecule. So a graph can be used to represent the structure of a molecule. So we can think of nodes as atoms and edges as their connections. So, we can think of the edges as the bonds between two different atoms. And in the molecule, we can have different types of bonds and different types of atoms. So a graph can also be used to represent social media networks. In the social media networks, we can think of nodes as users and edges as their connections. So we can use graph to predict some properties of each user or learn about their interactions or relationships. And a graph can also be used to represent a program. If you know the program's abstract syntax tree, for example, it is AST, that is a tree representation of the abstract syntactic structure of the source code, which is written in a formal language. So each node in the tree denotes a construct occurring in the source code. For example, in this AST, we have some nodes like while, and we also have a node called branch. Between while and branch, there is an edge called body. So different nodes are connected by edges, and there are different types of edges and nodes. So I list some examples of graph applications here. Besides molecule, social media networks, and programs, we can also use the graph to represent, to do some tasks like fake news detection, traffic prediction, or even applications in natural language processing, because we can also use graph to represent the text. We can manually define different relationship between different tokens in the text. So, so graph can be used in the tasks such as text classification, neural machine translation, and so on. And graph can even be used in computer vision field. It can be used to represent an image, because you can think of image as a matrix, and we can also represent a graph using a matrix. So a graph can also be used to describe different objects in the matrix, in the images, describe their relationships. We can manually define a graph to represent the image. So applications such as image classification and object detection and so on we can leverage graph on these tasks. So after talking about what can a graph represent, let's talk about the next question. How do we represent a graph? So there are the most common two methods to represent a graph structure is an adjacency matrix or a list of paired vertex indices. So the first method, we can use adjacency matrix to represent the graph. For example, in the right upper corner graph, there are 4 nodes, 1, 2, 3, 4. So the adjacency matrix to represent this graph, the size of it is 4 by 4. And we use 1 to denote the edge between 2 nodes. So for example, node 1 and 2 has an edge between them. So in the corresponding position in the adjacency matrix, we put the value 1. If there is no edge, we put the value 0. We can also put other values instead of 1 or 0 to represent different features or different types of the edges. So another method to represent the graph is a list of paired vertex indices. This is used when the adjacency matrix of graph is sparse. So this representation method will be more memory efficient. For example, the set of vertex V is 1, 2, 3, 4. So we can use the set of edges, the list of edges, to represent the graph as 1, 2, 2, 3, 2, 4, and 3, 4. So next, let's talk about what is graph neural networks. The graph neural network, GNN, are a class of neural networks that can be used to process data best represented by graph data structures, which means the GNN can be directly applied to the graphs. And it can provide an easy way to do either node level, edge level, or graph level prediction tasks. Graph neural networks operate by propagating neural messages between neighboring nodes. And at every propagation step of a graph layer, the neural network computes each node's sent message, and each node aggregates its received message and then updates its own representation by combining the aggregated incoming messages with its own previous representation. So formally speaking, we can have an initial representation of each node V in the graph as HV0. 0 means you can think of it as layer 0, which is the initial representation of a node. It belongs to RD0. D0 is the dimension of the node's initial representation vector. This representation is usually derived from the node's label or its given features. So then a graph neural network layer updates each node's representation given its neighbors, and we get a node's first layer representation, HV1. 1 is the layer 1. It belongs to RD. D is the dimension of the node representation in this layer, and it can be different from the dimension of the initial representation vector. So in general, the kth layer of a GNN is a parametric function fk that is applied to each node by considering its neighbors. We can look at the equation here. So the input of the parametric function fk is the node representation of V in the last layer k minus 1, and the representation vector of all its neighbors in the last layer k minus 1. So here, NV is the set of nodes that have edges to V, which means it is the neighborhoods of V. And theta k is the parameters in this parametric function. So in general, this layer is applied to each node by considering its neighbors, and it defines how to combine all the messages a node receives. And the design of this function f is what mostly distinguish one type of GN from the other. So first, let's talk about the graph convolutional neural network, which is the most cited neural network structure in the GNN literature and the most commonly used architecture in real-life applications. GCNs are similar to convolutions in images in the sense that the filter parameters are typically shared over all locations in the graph. At the same time, GCNs rely on message passing methods, which means that vertices exchange information with the neighbors and send messages to each other. Before looking at the math, we can try to visually understand how GCN work. So the first step is that each node creates a feature vector that represents the message it wants to send to all its neighbors. And in the second step, the messages are sent to the neighbors so that a node receives one message per adjacent node. So for example, the node 1 has its feature vector, and its adjacent node is node 2. After message passing, node 1 aggregates its own feature vector and the message from node 2. And for node 2, since it has 3 neighbors, 1, 3, 4, and itself, so after message passing, it will combine all messages from the 4 nodes. And the same is with node 3 and node 4. So we have an equation to represent the graph convolutional neural network, which is HV in the layer K equals to sigma and this. So the sigma is a nonlinearity activation function. It can be any activation function such as ReLU. And NV here is the neighborhood of node V. CUV is the normalization factor, which we often set it to be the square root of NV multiplied by NU, or the absolute value of NV. And WK here is the shared weight matrix in the kth layer. So we multiply the W and the H here to convert the node's representation of node U to its message, and then divide by this normalization factor to take the average of all the messages from the node itself with its neighbors, and then pass this value to the nonlinearity activation layer. However, we can see there is one issue here in this example. We can see the output features for node 3 and 4 are the same because they have the same adjacent nodes, including themselves. Therefore, graph convolutional networks layers can make the network forget node-specific information if we just take a mean over all messages. Multiple possible improvements have been proposed. While the simplest option can be using residual connections, the more common approach is to either weigh the self-connections higher or define a separate weight matrix for the self-connections. Next, let's talk about how to solve the problems in GCN. So we can introduce the attention mechanism. The attention describes a weighted average of multiple elements with the weights dynamically computed based on an input query and elements case. This concept can be similarly applied to graphs. So one of these such kind of GNN is called Graph Attention Network, GAT. Similar to GCN, the graph attention layer creates a message for each node using a linear layer. And for the attention part, it uses the message from the node itself as a query and the message to average as both keys and values. And the score function of the attention is implemented as a one-layer MLP, which matches the query and key to a single value, which is the score, the attention score. Once we obtain all the attention factors, we can calculate the output features for each node by performing the weighted average. So we can see the equation here. We can first look at the figure here. For the node 1, its node representation vector is H1. We will use attention mechanism to calculate the scores for this node and all its neighbors. So we got the attention score alpha for each node. And then we multiply alpha with the message of each node. So we take the weighted sum, weighted average of the node itself and its neighbors. And then we pass this value to the sigma function, which can be a nonlinearity activation layer. So this is graph attention network. So these are 4 kinds of GNN explored in this paper. They are very widely used. As we can see, different GNN are differentiated by their parametric function, which is the way to combine the messages a node receives and the message of the node itself. So, first, for the GC and the graph convolutional networks, we can see it takes the average of the message of its neighborhoods to calculate the node's representation. And the second type of GNN is called GIN, which is graph isomorphism network. It just add the node representation of all its neighbors and then add a parameters and then add itself and multiply by a coefficient and then pass this value to a MLP layer. And the third one is the graph attention networks. It uses attention mechanism to say which neighboring nodes is more important to the target node itself. And then the fourth kind of GNN is called gated graph neural network. It uses a GRU, a gated recurrent unit, to process the messages. So in this equation, the A is computed by aggregating information from different nodes via incoming and outgoing edges with parameters dependent on the edge type and direction. So GGNN use a GRU unit to update the hidden state of node V by incorporating A and the previous time step hidden state HK-1. Next, let's talk about the GN bottleneck, which is the topic of this paper. So as we have seen, a GN layer can be viewed as a message passing step, where each node updates its state by aggregating message flowing from its direct neighbors. And GN variants mostly differ in how each node aggregates the representations of its neighbors with its own representation. However, most problems also require the interaction between nodes that are not directly connected, and they achieve this by stacking multiple GN layers. So different learning problems will require different ranges of interaction between nodes in the graph to be solved. We call this required range of interaction between nodes the problem radius. So its definition is the range of interaction between nodes. In practice, GNNs were observed not to benefit from more than few layers. The accepted explanation for this phenomenon is called oversmoothing. The definition of oversmoothing is that the node representations become indistinguishable when the number of layers increases. However, oversmoothing was mostly demonstrated in the short-range tasks. Short-range tasks are tasks that have small problem radius, where a problem correct prediction mostly depends on its local neighborhood. Since the learning problems depend mostly on short-range information in these datasets, it makes sense why more layers than the problem radius might be extraneous. In contrast, in tasks that also depend on long-range information, this paper hypothesized that the explanation for limited performance is called oversquashing. So the main contribution of this paper is to introduce the oversquashing phenomenon. This is a novel explanation for the major and well-known issue of training GNNs for long-range problems. And this paper will also show its harmful practical implications. So what is oversquashing? To allow a node to receive information from other nodes at a radius of k. K is the number of layers, and R is the problem radius. The GNN needs to have at least k layers, and the k layers should be larger than or equal to R, which is the problem radius. In reality, the problem radius R is generally unknown in advance, and it is usually approximated empirically by tuning the number of layers k. So the requirement is k should be larger than or equals to R. Otherwise, it will suffer from underreaching problem. The underreaching problem is that the distant nodes will simply not be aware of each other. So it is clear to avoid underreaching problems that depends on long-range interaction. Require as many GN layers as the range of interaction. However, as the number of layers increases, the number of nodes in each node's receptive fields grows exponentially. This causes oversquashing. The information from exponentially growing receptive field is compressed into a fixed length node vector. This is called oversquashing. In the consequence, the graph fails to propagate messages flowing from distant nodes, and it will only learn short-range signals from the training data. If the model learns only short-range signals from the training data, it might consequently generalize poorly at test time. In fact, the bottleneck is very similar to the bottleneck of sequential RN networks as shown in this figure. So traditional sequence-to-sequence models suffered from a bottleneck at every decoder state, which means the model had to encapsulate the entire input sequence into a fixed size vector. And in RNNs, the receptive field of a node grows linearly with the numbers of recursive applications. However, in the graph neural network, the bottleneck is explicitly more harmful because the receptive field of a node grows exponentially. As we can see in the figure, the red arrows means the receptive fields of a node. It can grow exponentially. So let's consider an over-squashing example, which is called the neighbors match problem. So in this figure shown here, the green nodes A, B, C have a different number of blue neighbors. For example, node A have 3 blue neighbors, and node B only have 1 blue neighbors. And each green nodes also have an alphabetical label. Each example in the data set is a different graph, which has a different mapping from the numbers of neighbors to the labels. And the rest of graph in the middle of this figure represent a general unknown graph structure. So the goal of this problem is to predict the label of the target node, which is labeled with a question mark. So the label should be the number of its blue neighbors. The correct answer for this example here is C, because in this case, the target node has 2 blue neighbors. And we can see that node C also has 2 blue neighbors. So the label for this target node should be C. Since the model must propagate information from all green nodes before predicting the label of the target node, we can see a bottleneck at the target node is inevitable. This bottleneck causes over-squashing, which can prevent the model from fitting the training data perfectly. Let's compare the short-range and long-range problems. A short-range problem is a problem that only needs to consider its local neighborhoods. But for long-range problems, a correct prediction requires considering the local environment of a node and interactions beyond the close neighborhood. So this paper will then explore problems in the long-range problems. Next, let's look at the evaluation part. The first section of evaluation is the synthetic benchmark, which is the neighbors match problem we have just seen. So the neighbors match problem is a contrived problem that they designed to provide an intuition to the extent of the effect of over-squashing. This manually designed problems allowing us to control the problem radius R, and thus we can control the intensity of over-squashing. This paper focuses on the training accuracy of a model to show that over-squashing prevents models from fitting long-range signals in the train set. So we can see the example figures here. The paper converts the neighbors match problem to represent as a binary tree, where the depth of this tree is k and the problem's radius is r. In this case, we can see problem radius r equals to the depth of the tree k. So the goal is to predict the label of the root node with the question mark by learning the messages passed from all the leaves in this tree, which the leaves are the green nodes. So in this case, the label of the root node is C, which has two blue neighbors. So they implement a network with R+1 graph layers to allow an additional nonlinearity after the information from the leaves reaches the target node. So the results shown here, we can see that some GNNs fail to fit the data set from starting from R equals to 4. For example, the training accuracy of the graph convolutional neural network at R equals to 4 is 70%. And at R equals to 5, all GNNs fails to perfectly fit the data. Starting from R equals to 4, the model suffered from over-squashing that results in underfitting, which means the accuracy becomes very low. And the bottleneck prevents the models from distinguishing between different training examples. These results clearly show the existence of the over-squashing problem in training GNN starting from R equals to 4. So let's consider why did some GNNs perform better than others. As we can see here, clearly GGNN and GAT performs a little bit better than GIN and GCN. So the explanation is that GCN and GIN managed to, so we can say they managed to fit R equals to 3 at most, while GGN and GAT also reached 100% accuracy at R equals to 4. So this difference can be explained by their neighbor aggregation computation. So we can consider the target node that receives message in the R step. So GCN and GIN aggregate all neighbors before combining them with the target node's representation. So therefore, they must compress the information flowing from all the leaves into a single vector, and then will only interact with the target node's own representation. And in contrast, GAT use attention mechanism to weight incoming message given the target's representation, and GGNN use GRU cell to filter incoming edges as GAT. So we can say GAT and GGNN use some mechanism to know which neighbors nodes should I consider more. So at the last layer, the target node can ignore the irrelevant incoming edge and absorb only the relevant incoming edge for GAT and GGNN. So in this case, the node representation at the last layer will only contain information flowing from half of the leaves, which means a single vector compresses only half of the information. So GAT and GGN performs better than GCN and GIN. And another question is, how do since all GNNs reached low accuracy at last in our in this experiment, how do GN-based models usually fit the training data in the public data sets of the long-range problems? So their hypothesis is that they overfit short-range artifacts from the training set and thus generalize poorly at the test time. Next, let's look at the real-life data sets. The second experiment is on the data set of QM9. So how to measure over-squashing problem in the real data sets? Instead,
sorry, I have a question.
Okay, sure.
From the previous slide,
Yes.
their hypothesis is that GNN-based models generalize poorly at test times. So is that a fact? Is that a well-known fact that all GNN have like low generalizability?
Yes, I think the author means that in real applications, when we use GNN for training, at least currently the performance the GNN achieves usually generalize poorly at test time. At least it does not generate as good as the training set.
Okay, I see. Thank you.
Yeah, sure. So how to measure the over squashing problem? Instead of measure over squashing, they measure whether breaking the bottleneck improves the results of long-range problems. So how to break the bottleneck? What they do is that they add a fully adjacent layer. So they took the tuned models from the previous work and modified the adjacency in the last layer, which means given a GNN with K layers, they modified the Kth layer to be a fully adjacent layer, which is called FA. So a fully adjacent layer is a GNN layer in which every pair of nodes is connected by an edge. So for this data set, each graph is a molecule where nodes are atoms and undirected typed edges are different types of bonds between the atoms. So the goal is to classify each graph to some real valued quantum chemical properties. The data set contains about 130,000 graphs, and each graph contains about 18 nodes. This is a graph level prediction. For the models, they use the existing model, which performs best when the number of layers equals to 8. This can tell us that this is a long-range tasks because the layer is equals to 8. And so they use the existing as the base models to compare their retrained model, which is added a fully adjacent layer. The results is shown here. The main results are that breaking the bottleneck by modify a single layer to be a fully adjacent layer significantly reduces the error rate by about 42% on average across all the GNN types. And these experiments clearly show that show the evidence for a bottleneck in the original GNN models. And these are also the results for other types of GNNs. So we can ask some questions. The first question is, so we have seen the performance improvement by adding a fully adjacent layer. So for the previous existing model, the performance is not as good as when we break the bottleneck. So is the bottleneck caused by the over squashing or underreaching problem? What is underreaching problem? The the underreaching problem is that we don't have enough layers to propagate all the needed messages for each node. So to answer this question, we measured the graphs. They measure the graph's diameter in the dataset. The diameter is the maximum shortest path between any two nodes in a graph. They find that at least 90% of the examples in the dataset do not suffer from underreaching problem because the number of layers was greater or equal than the diameter. So they conclude that the source of improvement was clearly not the increased reachability, but instead the reason is the reduction in oversquashing. And the second question is, can larger hidden size achieve a similar performance? So they use a hidden layer. They set the hidden layer size of the double size of the previous one, which is 2D. So these models, we can see these models achieved only 5.5% improvement over the base model, while adding the fully adjacent layer achieved about 42% improvement using the original dimensions and without adding weights. So we can see it is not to double or make the hidden size larger to achieve a similar performance, but to add a fully adjacent layer, which is to to break the bottleneck of the over-squashing problem. And the third question is that they explored is the entire fully adjacent layer needed? So this is their experiments. They experimented with using only a sampled fraction of edges in the fully adjacent layer. So as the results shows, when the fraction of added edges is larger in the last layer, the decrease in error will be larger. For example, using only half of the possible edges in the last layers still reduce the error rate by 31.5% on average compared to the base. And the last question is, if all GNNs benefit from direct interaction between all nodes, maybe the graph structure is not even needed. They explore this question by training another set of models where all the K layers are fully adjacent layers instead of using the graph topology. But they find that this model produce 100 and 500% higher error. So this means we still need the graph structure to represent the data. The third section in the evaluation is explored in the biological benchmarks. This benchmark contains two data sets. One is called NCI1. It contains about 4,000 graphs, and each graph contains about 30 nodes. And its task is to predict whether a biochemical compound contains anti-lung cancer activity. And another data set called enzymes. It contains 600 graphs with 36 nodes on average. And its task is to classify an enzyme to 1 out of 6 classes. So their base models are that for NCI1, they use GIN, which is proved to achieve the best state-of-the-art performance on this data set. And for enzymes data set, previous work find that no graph topology is better for this data set. So in this paper, they compare the performance between existing base models with their retrained model, which is added of a fully adjacent layer. The results are shown here. So the main results are for NCI1 dataset, the GIN with fully adjacent layer improves by 1.5% over GIN base model, which was previously the best performing model. And for enzymes dataset, previous work found that none of the GNs exploit the topology of the graph. But this paper find that when adding a fully adjacent layer to GIN, this model does exploit the structure of the graph and improves the performance by about 8.1% over GIN-based model. And it improves by 2.5% over the no-struct model. On average, models with fully adjacent layers relatively reduce the error rate by 12% in enzymes and by 4.8% in NCI1 dataset. These experiments clearly show that there is evidence for a bottleneck in the original GNN models. The last benchmark they use is called VAR misuse, which is a benchmark targeted at the programs. So this data set is a node prediction. This is a node prediction problem that depends on long-range information in the computer programs. And the best results were previously were found using 6 to 10 layers, which indicates that this is a long-range problem. So they also compares the existing base model with their retrained plus FA model. The main results is that adding a fully adjacent layer to all the GNNs improves their same project accuracy, as can be seen here in the table. This obtain a new state-of-the-art of 88.4% of accuracy. And in the unseen project set, adding a fully adjacent layer improves the results of some of the most of the GNNs, which obtains a new state-of-the-art of 83.8%. So all these experiments show the existence of the bottleneck in the GNN and show the over squashing phenomenon. Next, let's talk about the related work in this field. So there is some existing work that talks about the underreaching problem, which I have mentioned before, which is the underreaching problem is that it is unable to be aware of nodes that are further away than the numbers of some numbers of layers. However, even when the information is reachable within the edges, we show that this information might be over-squashed along the way. Thus, the over-squashing limitation described in this paper is tighter than the under-reaching problem. And there are also some existing work that talks about over-smoothing problems. So node representations become indistinguishable and prediction performance decreases as the number of layers increases. The explanation is over-smoothing. This might explain the empirical optimality of fewer layers in short-range tasks, for example, for tasks with only 2 layers. But some problems depend on longer range information propagation and thus require more layers to avoid underreaching. So in this paper, they hypothesized that in long-range problems, the explanation for the degraded performance is over-squashing rather than over-smoothing. There are some previous work that explores how to avoid over squashing by various profitable means. So some work add virtual edges to shorten long distance, and some work add super source nodes to avoid this problem. And other work designed program analysis that serve as some shortcut edge types. However, all this existing work do not explicitly explain the solutions using over squashing, and they did not identify the bottleneck and its negative cross-domain implications. So in this paper, they propose a novel explanation to a well-known limitation in training graph neural network, which is a bottleneck that causes over squashing problem. For tasks that depend on long-range interaction, require as many GN layers as the desired radius of each node's receptive fields. This causes an exponentially growing amount of information to be squashed into a fixed length vector. So as a result, the GN fails to propagate long-range information, and it learns only short-range signals from the training data instead. And GN also performs poorly when the prediction task depends on long-range interaction. So this paper showed that GCN and GNN neural network structures are more susceptible to over squashing than GAT and GGNN. And they also show that prior models of chemical, biological, and programmatical benchmarks suffer from over squashing by showing that they can be dramatically improved using a simple fully adjacent layer. So they conclude that over squashing in GNN is very prevalent and untreated in some benchmarks, that even the simplest solution, such as adding a fully adjacent layer, helps. So the further work can be to explore a variety of follow-up improvements of such over squashing bottleneck and even better solutions for the over squashing. Thank you.
Okay, so any questions?
Hi, I have a question.
Sure, go ahead.
Okay, it's about the fully adjacent layer. So I'm kind of lost in their logic because I think it goes back to what the bottleneck actually means, because I don't think I fully understand what is the difference between over squashing and probably over smoothing, and aren't adding a fully adjacent layer just the same as adding the bottleneck? Because in my understanding, they are trying to claim that because of the aggregation of so many nodes, and that is the cause of over squashing, but the fully adjacent layer actually include all the edges. So aren't that, if it is a very dense network, aren't that just going to cause even more bottleneck problem?
Yes. So as you can see, for the over squashing problem, they break this bottleneck by adding a fully adjacent layer. For example, in the graph, we have k layers. So the k layers is the fully adjacent layer they used, and the k-1 graph layers has already exploited the graph structure using their original graph topology. And only the kth layer, the last layer, which is a fully adjacent layer, this layer allows the topology aware node representations to interact directly and consider nodes beyond their original neighbors. So they hope that this action, by adding a fully adjacent layer, could ease the information flow and prevent over squashing, and thus reduce the effect of the existed bottleneck. So this is why they add a fully adjacent layer. They just assume that but intuitively, by adding this fully adjacent layer, this action can ease the information flow. And so different from over smoothing. Over smoothing is a problem when for some problems that only needs to consider local neighborhoods. It does not needs to consider the long range nodes of a certain node. So in such problems, we don't need to use many layers. So only a few layers is enough for the short range problems. So if in this problem, if we add more GN layers, over smoothing will cost, because the information would be too much for such a small range problem.
Okay, I see, but goes back to the breaking the bottleneck. So what is exactly the definition of the bottleneck? Because it is still like a bit confusing to me that aren't fully adjacent layer actually will further increase the bottleneck problem.
Oh, okay. So to explain what is the bottleneck, the bottleneck is that in the problems of in long range problems, in the problems that requires long range information, we use many GN layers. We stack many layers to propagate the distant message, the message in the longer distance. So so a node will receive messages that combines the messages from a very long distance. So
so can I interpret as they are more focusing on the depth of the neural network and not the aggregation part?
Yes. So to some extent, I think it is also relevant to the aggregation part, because in the experiments we see that if the aggregation is to use some attention mechanism to identify which information is more important, then the model can have better performance. So both the layers of the networks and the aggregation matters for the long range problems.
I see. Yeah, but actually for the aggregation part, the fully adjacent layer didn't actually solve that, right? Because it have that single layer have to aggregate all the agent information, right?
Yes, but because the fully adjacent layer is the last layer, so I think it is to combine again all the messages from the neighboring nodes or further distant nodes together to remain the messages from them.
Okay.
Yes.
Okay, so I also have a follow-up question that aren't this just the just like the residual connection in convolutional neural network? So it is kind of a well-known problem already, right? So what are they proving here? So it is like, to me, it looks just like gradient vanishing. and so that their fully adjacent layer is just to add a residual connection just directly to the output layer. So kind of to me, of course, they're going to perform better because their other networks didn't add these kind of connections.
So do you mean that there is residual connections in GCN?
No, I mean like their idea of adding that fully adjacent layer, is that just like adding a residual connection in convolutional neural network, because it includes like all the edges. So
yeah.
So to me, it kind of is unfair, right?
Yes, I think it is true, but they just want to use a very simple way to kind of solve this this over squashing problem. Yeah, because it is very intuitive.
Okay,
like it's not exactly like adding a like skip connection, because like when you add this like full adjacent layer, you basically do like in the end when you're doing the final whatever like classification or just like the final goal of the network, when you're just like determining what the result is, just not only consider the node that you're working on, but also all the other nodes. So your node, the main like root node, do not need to contain all the information about the whole graph, but everyone can store their own information. And then you just do like a fully connected layer in the end that just maps all the information from all the nodes to the end. For example, in this case, if we are looking for like the first like synthetic problem to understand like how many adjacent nodes a node has, and then just like label them accordingly, everyone can hold, for example, all the nodes can hold an embedding that would show how many nodes they have. And in the end, this fully adjacent layer would just compare what the target node, for example, has in common with all the other embeddings, and just like find, for example, the most similar embedding, and then just like say, okay, this is the most similar one to this, and we're just gonna give the label of the most similar other node, for example. That would be kind of the function of the last node. So otherwise, if you don't have this kind of a fully adjacent node, fully adjacent layer, then all this information about like all the other nodes need to be collected in single node. So it somehow like does actually prevent this like bottleneck problem. It's not exactly, I don't see it exactly like a skip connection, because in the skip connection, like you add a connection to the previous stages, previous time stamps of the node. We're just like, I mean, it's more like I see skip connections as a connection between the previous timestamps and the next like current timestamps, but the fully adjacent layer is more like in the width, actually, a skip connect in the width more than in the depth of the layer.
Yeah, but aren't that but in my opinion, like because the graph neural networks are already like with much less layers compared to other kind of network. So this the fully adjacent layer that use the original input itself looks kind of like the skip connection, right? Because there are like just a few layer difference.
To me, it doesn't look like a skip connection. Rather, it looks like we are just like increasing the width of the layer, the width of the network in the last layer, because you don't actually like get connected to previous layers. You just don't add a skip connection from previous layers, rather than, so it's not like the final goal is very loosely connected to the nodes in the last layer. So you just add connections from all the nodes in the last layer, all the neurons, so to say, in the last layer to the final goal. So it's more like you just like connecting, like making the last layer fully connected rather than like loosely connected.
So the fully adjacent layer only includes the edges from the nodes in the last layer?
Yes, right.
Oh, I thought it includes like all the edges in the network, like in the graph.
Include all
It's
the
not-
edges, but like all the edges in like still like this neural network, like it's not like the edges are not like the previous stages. They're like, so we can imagine like graph neural network as a like multi-layer fully connected, for example, where some connections are missing, and then each like edge has at each node at each time step is like a neuron, and the time steps are the layers.
Yeah,
So-
I see. Yeah, that indeed is
how
not like skip connection.
Yeah, you're only like connecting everything in the last layer to the final output.
Yeah, I see. Okay, thank you.
Yeah, thank you.
Yeah, so for this question, we also have some follow-up comments. Can we go to a page with figure comparing the GN with LSTM or recurrent neural nets?
Yes.
They have a figure to illustrate the concept, right? So as shown in this page, I mean, so for the graph neural nets, and when we do the propagation or aggregation of information, and so not for the last layer, we have to accept the information from the neighbors, right, for learning the node representations. And it defines one at the bottleneck. I think this one is more like a artificial concept, right? So it defines one at the bottleneck for the graph neural nets. And to address this problem, I think they add the layer for the called fullness adjacency layer, right? This is more like, broaden the last layer of the bottleneck, right, to access all the nodes in the graph as neighbors for the target node, right, for learning the representations. So in some sense, it is very similar, or you can model this one as like a higher way connection among the target node to other nodes in the graph, right? Even though they accept the information for the native or for the last or for the second last layer representation for the aggregation, right? In some sense, it's similar to the residual learning. Oh, of course, it's not exactly the same, right? It's similar to the residual learning, actually. This kind of thing, I mean, because according to this paper, it seems to be useful. The main reason is because the data set of the experiment they are doing is more like a graph level classification or matching problem, right? So when it comes to some other problems, I cannot guarantee this technique will be useful, actually. Because if for a node we access all the nodes representations for learning its representation, then there will be so much noise information to come in, right? We cannot guarantee like when we learn the representation for me in Facebook, and we also access all the nodes like someone in Europe, in Africa, learning and get the information to learn my representation, then it will be quite noisy. Right? So I think this technique can only be useful for the graph level representation or graph level classification tasks. When it comes to node level classification, I don't think this one will be useful, right? Because it will be so noisy. You access all the information nodes, all the nodes information for learning representations. We don't want to accept this much information actually in the application for node classification task. Right? We only want to accept the local information, I mean, for learning the representations. It really depends on the task, I mean, to decide if this technique is useful or not. In some sense, it is quite similar to the showing, right? You mentioned, in some sense, it's like the higher way connection. So even though it's not exactly the same as the learning we used before for other models, right? Yeah, this is just a follow-up comment for this question.
Yeah, thank you.
Thank you.
Yeah. Any more questions?
I have a question.
Mhm.
So is it like is it used in any further papers like this? So they've explained it well, but are there any applications of it as of now? Were you able to check them out?
Do you mean, is there any further solutions for this bottleneck? Other
Yes,
than,
yes. They
um,
said in the paper, I remember them saying that now this is like one way to explain the bottlenecks in graph neural networks, and this could be used as a further explanation, and it could be derived upon. So are there any, I'm just wondering, like, so one thing that he said in the paper was even the state-of-the-art models were not able to, and in the presentation he also said they were not able to perform very well when they were tuned a bit. So is it like any new things came or not? Like that? It's just like is there anything that was there? Were you able to find?
So actually, I'm not very sure about the following works of this paper, but as we can see, there are some existing works that kind of solves the limit of this the GNN training problem, which is over squashing, but I'm not very sure about if there are some new current work that provides some more technologies other than just adding a fully JSON layer to solve over squashing. But I think this is a good question, and I think it's interesting to explore. Yeah.
Thank you so much.
Yeah,
A good presentation.
Thank you. Thank you.
I have an open question.
Sure.
Yeah, how could they find the over squashing is a problem, and also how did they find this problem?
Yeah, I think this is a very interesting question. I think they must have some thoughts of the so there are some common sense that there are some limit of training the GNN models. So there are some existing works that propose some explanation of why training GNN is hard, or why there is some bottleneck in GNN. So existing explanation is over smoothing, but over smoothing can only explain the problems which only needs short range information rather than long range information. But as the GNN is more widely used, more applications that requires long range information will need GNN to process them to finish the task. So how to explain the training problem in GNN they propose different from short range problem. For long range problem, the explanation for the limit is called over squashing. So they provide this concept, or I think they first provide a hypothesis and do experiments to prove that their hypothesis is right. Yeah.
Thank you very much.
Sure.
Yeah, any more questions from students? Okay, if there is no question, I think that probably that's it for today's class. And this paper actually, how to say, I mean, they define a concept, or however, the definition of this concept is not very clear actually. They name this kind of over scratching or bottleneck as a concept. However, they fail to provide a quantified concept definition of this term. So it's hard to say what is over scratching and what is bottleneck for graph neural nets. This is according to my feeling for this paper. And anyway, I think they propose a new term and for us to analyze when we study the graph neural nets. And you can also check if these kinds of phenomena also exist or not when you are doing research about graph neural nets in your applications. And the talk is pretty good. And thanks so much, Riton, for the talk and for the discussions. And
Thank
for
you very much.
students, do you have any more questions? If there's no question, then probably that's it for today's class. Thanks so much for your time. Also for students, if you don't know the GC and GAT or the over smoothing problem yet, then you may refer to the reference list we provide you, I mean, for the course. We'll provide you with some papers about graph neural nets as well in the reference list. You can also check these papers by yourself at the class as well. Oh, thanks so much, Rita, for the talk.
Okay, thank you.